Let's say we have a vector space V, and inside that vector space is a subspace H, and there are vectors in the subspace V, and we want to know if these vectors are a basis for the subspace. It could also just be in V. Basis is how you construct all your vectors, basically. So there are two conditions. It has to span the space, and it has to be linearly independent. So if you have like B1, B2, Bn, etc., you're going to have this linearly independent solution set that equal to 0. Remember, this is only linearly independent if C1, C2, all the way to Cn are equal to 0, because that's the only way for us to get the 0 vector. If there were non-trivial ways to combine these vectors, like in such a way that we didn't get a 0 vector from having non-zero constants, then we would have linear combinations of these, and they would not be linearly independent, they would be linearly dependent. And remember that the span is the set of vectors b1, b2, bn, and it is the set of all possible linear combinations of these. So we're going to have C1, B1 plus C2, B2 plus yada yada yada, Cn, Bn. But that doesn't necessarily mean that it's 0. And we say that this could be equal to some other vector. Oh, not 0. My bad. Some other vector, let's say, call it x. That is basically what the basis is. The basis is the building blocks to your vector space. If you're in R2, or two-dimensional space, you have two basis vectors, 1, 0, and 0, 1. This is the standard base. I'm not going to really talk about other bases, but as long as these two vectors are linearly independent, another basis could be, say, 1, 1 and 1, negative 1. Ooh. 1, negative 1. These are also linearly independent, and they would span the space just as 1, 0, 0, 1. R3. Ooh. What's going on? R3, the standard bases are 1, 0, 0, 0, 1, 0, and 0, 0, 1. And these are all part of a set, like that. But you could easily have 3 other vectors that are linearly independent. 1, 2, 0, 0, 1, 3, and say 4, 5, 6, which would also satisfy a basis, I guess. I think. Not sure. And this can also extend to other vector spaces, say for functionals and polynomial space, and even matrix space. Although I'm not really sure about functional and polynomial space, but for the standard 2x2 matrix, the standard basis would be this set of these four matrices. Because you can combine these into like linear combinations and make any sort of matrix out of it. I thought it was really cool, really neat and interesting. But typically when you look at basis, you're going to be looking at R2 or R3. And let's say if we have three vectors, let's say we're in R3. We have three vectors, and we want to know if it's if it forms a basis in R3. How do we tell? Well, we're gonna put it into a matrix. So let's say say 2, 1, negative 3, 4, 7, 5, 2, 3, 2, 8. So what you do is you put this into a matrix. 2, 1, negative 3, 4, 7, 5, 3, 2, 8, and then you row reduce. And row reducing this gives the identity matrix, which gives us the row space 1, 0, 0, 0, 1, 0, 0, 0, 1. So we could say that V1, V2, V3 do make a basis in R3. And that's about it for basis. I'm not going to really cover change of basis, or maybe I am. I don't know. I don't think I have it in my notes at all. I didn't really find it that important, but I'm sure it is. If anyone wants it, I'll do it. Alright, see you later.